This is slide number 42 and I am your presenter Asloob Mudassar. Wave propagation in Fresnel and Fraunhofer domains. In earlier discussion, the point of observation was located many optical waves from an aperture or from an object. Here we generalize the discussion for the point of observation to be located beyond the limit of many optical waves to infinity. This region from many optical waves to infinity has been divided into two domains referred to as Fresnel and Fraunhofer domains. Scalar diffraction formulas in these domains or in these regions or domains are obtained under certain approximations applicable to the scalar diffraction formula derived in earlier discussions. So we have to use some approximations, in order to obtain the Fraunhofer and the Fresnel field of diffractions. These approximations are specifically known as Fresnel and Fraunhofer approximations. Derivation of Fresnel and Fraunhofer diffraction formulas supported with some practical examples will be presented. So we shall do the derivations of Fresnel and then the Fraunhofer diffraction formulas, and we shall also evaluate some examples that fall in these two domains. So now let's talk about the Fresnel diffraction formula. Rayleigh-Sommerfeld solution is reproduced below. You see that before that we have three formulas for the Fresnel diffraction formula. Now and we are using one of them, which is the Rayleigh-Sommerfeld solution 1, and we are reproducing it below. So in equation 1 we have the Rayleigh-Sommerfeld solution 1, and you know that this u of p naught is actually the field at the point of observation p naught. And you know that on the right hand side you have a over iota lambda double integral over the surface S1, and S1 is actually the clear aperture in which the point P1 is located, and we have e to the power iota k r within the bracket r01 plus r21 divided by r01 r21 multiplied by chi and the surface element ds. And you know that r01 was the distance of the point P1 from the point P0. Point P0 is the point of observation and point P1 was located within the clear aperture, and r21 is the distance of the point 2, which is the point source generating spherical waves, and from the point P1 which is located on the clear aperture. So this is what we have mentioned we have given very much details about these formulas earlier. And you know that in the second line we have the explicit dependence on the field at the point P1. So we have this u of p naught is equal to 1 over iota lambda surface integral over S1 u of P1, that is the field at point P1, multiplied by e to the power iota k r01 over r01 and cos of n comma r01 and ds. You see that this cos is actually replacing the chi in the first line. So this formula is also known as the Huygens-Fresnel diffraction formula. P1 are the secondary fictitious point sources located within the clear aperture. P0 is the point of observation at the distance r01 from P1 lying on the xy plane. And u of P1 is equal to a e to the power iota k r21 over r21 is the contribution at P1 of a point source located to the left of the clear aperture at a distance r21. So that is over this is the contribution of the source point at the observation point P1. So cos of n comma r01 is the cosine of the angle that the vector joining P0 to P1 makes with the surface element n which is at point P1. So u of P1 e to the power iota k r01 over r01 are the fictitious point sources located within the clear aperture. The planar diffracting aperture coincides with the zeta eta plane at z is equal to 0 with the clear aperture indicated by the surface capital S1. The xy plane is labeled parallel to the eta zeta plane at a distance z capital Z from it. So we have the plane which is the xy plane, it is parallel to the zeta eta plane, and this xy plane is located at a distance capital Z. Both planes are piercing the z axis perpendicularly. So the field at the point at the zeta eta plane is known. We want to find the field at the point P0 which is located on the xy plane. So this is our problem. From the geometrical description shown, we can write cos of n comma r01, that is the angle between the normal to the surface, and the r01 is equal to cos of theta, which can be shown, which is shown in the figure, is equal to z over r01. So r01 is actually the radial distance between the point P1 and P0, where r01 is given by, so you see that we have the coordinates of P1 and P0. The coordinates of P1 are xi, eta and 0, whereas the coordinates of the point P0 are x comma y comma z. So we have applied the distance formula between the point P1 and P0, and r01 is given by the square root of x minus zeta whole square plus y minus eta whole square plus z square. So this is equation number 3. Using equation 2, equation 1 takes the form. So you see that we have the equation number 1 again written in this form: u of x comma y is equal to z over iota lambda surface integral over the surface S1 u of zeta eta and e to the power iota k r01 over r01 square and d zeta and d zeta. You know that here u of zeta and eta is actually the field at the clear aperture. So at the clear aperture at the point zeta and eta. So this is the same as u of P1. So we have replaced in the previous formula u of P1 by u of zeta and eta, which is the field at the input plane at the coordinates zeta and eta. The rest of the quantities are explained earlier. Now if z is greater than the maximum value between the difference of the coordinates, between the difference of the two coordinates, one on the xy plane, the other one on the zeta eta plane, that is x minus zeta, the absolute value and the maximum value of that quantity, if over z, that is the distance between these two planes, is greater than this quantity, and if z is also greater than the maximum value of the difference between the y minus eta coordinates, the right hand side of equation number 3 can be expanded into binomial series, keeping the first two terms of the expansion as given below. So in equation number 5 we are going to expand the equation number 3. The expansion is very simple. You know that the simple calculation from the simple calculus applying the binomial theorem or binomial series over here. So you see that we are keeping only the first two terms of this formula. The other terms are not important, and we shall explain these terms there. So you see that this is the Fresnel approximation. So this approximation, in which we keep the first two terms of the binomial expansion, is referred to as the Fresnel approximation, and the formula, the diffraction formula, which will be based on this Fresnel approximation, will be called Fresnel diffraction formula. So you see that we are also writing these approximations that we have done over here, that is inequalities, that z is greater than the absolute value of x minus zeta, the maximum value of that one, and similarly z is greater than the maximum of the absolute value of y minus eta. So we are writing these two in the following form, that is x minus zeta, the maximum value of 1 divided by z is less than 1, and similarly for the y variables. And you know that if you take the square of this quantity on the left hand side and also on the right hand side, you will see that x, we need to then remove the modulus sign, because we are talking about the square of that quantity. So x minus zeta divided by z is now less than 1, because this quantity is always less than 1. So if you take the square of that one quantity, so we need to put the double sign for less than, so less than 1. And similarly for the variable y we can write. So here you can say that we are writing that y minus eta over z whole square, the maximum value of that one is less than 1. The third term in the expansion, we have not shown the third term over here in the equation number 5, but here we want to talk about the third term. So this is the third term. You know that 1 over 8 curly bracket square, and within the curly bracket we have x minus 0 over z whole square plus y minus eta over z whole square, and that quantity is less than 1. We set now r01 is equal to z, the first term in the expansion. So R01 which will lie in the denominator, for the denominator part we shall replace only it by the first term, because we do not want to include the second term or the third term is that one, because we don't want to write an ugly expression. Moreover this is just only the amplitude, and the amplitude will not disturb the whole story. So this is the first term in the expansion. Replace R01 square in the denominator of the equation number 4 by z square. So R01 in the denominator will be replaced by z square only. The second and the higher terms in the expansion would not change the significance of the result, as R01 square only contributes towards the amplitude inclusion and inclusion of second and higher order terms will only make the appearance ugly. So we set R01 is equal to z plus 1 over z, and within the curly bracket we have x minus zeta whole square plus y minus eta whole square. These are the first two terms in the expansion. So replace R01 in the e to the power iota k R01 expression, that is in the exponent of e to the power iota k R01. We replace R01 by the first two terms that we have shown over here. So k being a large number, k R01, k multiplied by R01 has a significant contribution towards the phase at the point of observation. So you see that as R01 will be much smaller than, but if you multiply, because you know that over here e to the power iota k R01, here R01 is multiplied by k also, and k is a very large number. In that case we can say that k R01 should be such that the significant contribution towards by it, k being a large number, k into R01 has a significant contribution towards the phase at the point of observation. We are neglecting the third term in the expansion, assuming that the phase variation due to it is negligible, a small fraction of a radian. So let's analyze the third term. So this is the third term that we have written over here. So this is the third term, you know that, and what we are going to do is that we are going to write it again this term over here in equation number 6, but now we are going to multiply the k and z over here. So this is we have multiplied only on the left hand side by k and z, and you know that now this is only less than 1. Before that it was less than 1. So 4 less than sign symbols were used, but in equation number 7 we have used only the 2 symbols, because k is a very large quantity, and of course capital Z is also a large when you move away from the diffracting aperture. So Z will increase, and k you know that already has a large value. So you know that due to these two numbers which are large in number, when multiplied on the left hand side will make the inequality to hold only two less than symbols. So we have in equation number sign only two inequalities less than 1. Okay. This restricts the value of z and the region in space. Due to the restriction on z that ensures a negligibly small contribution of phase is known as the Fresnel region, and the scalar diffraction formula applicable to the Fresnel region is known as the Fresnel diffraction formula. So you see that in this equation z is very important. If z becomes very large, then you know that this inequality, double inequality, will be converted into a single inequality, and you know that the phase becomes significant, and we have to include the contribution of this term also. So in order to neglect the contribution of this term also, we have to restrict the value of z. Z should not increase much, so that there should be double inequality sign of less than equality sign from 1. So z is restricted in some way. That value of z which we are restricting is actually limiting the region to the Fresnel region. So, and the formula based in which we don't use the third term given by equation number 7, the formula is called Fresnel diffraction formula. Under the Fresnel approximation, equation number 4 takes the form. So you see that this was equation number 4 we have written. Now under these approximations, that is introducing R01 in the exponent term by the first two terms, and R01 in the denominator only by capital Z. Let's see what we get at the end. So we have this formula at the written in equation number 8. This is the formula under the Fresnel approximation, and you know that it is the form of equation number 4 when we used the above when we expanded the R01 into the first term for the denominator and the first and the second term for the numerator. So this is the formula that we have obtained. You know that this formula is referred to as the Fresnel diffraction formula. As u of zeta eta is equal to 0 in the opaque region of the diffracting aperture, no light source exists in that aperture. We can neglect the limits of this integral. We can extend or we can change the limit of this integral from minus infinity to plus infinity. So you see that here in equation number 8 we are writing just that the integral over the surface is only on the surface S, which contains only the clear aperture. But you know that in equation number 9 we have included the clear aperture as well as the opaque aperture. That's why we have extended the limit from minus infinity to plus infinity. And you know that in the opaque region, when we derived the Sommerfeld diffraction formula 1, we used that u is equal to 0 in that region, and the partial derivative of u was not 0, but the u was 0 itself. So you know that under that condition the formula was derived, and the equation and the formula in equation number 9 is extending from minus infinity to plus infinity, including both opaque region and the clear aperture. So equation number 9 is actually the true formula, which we can say that it is the Fresnel diffraction formula. To convert this to the convolution integral, we introduce the following term. So let's introduce, in order to write this formula in the convolution form, we are introducing a kappa of x comma y is equal to e to the power k z divided by iota lambda z, which is the constant quantity in equation number 9 on the left hand side of the integral, multiplied e to the power iota k over 2z, and within the bracket we have x square plus y square. So you know that if you replace in equation number 10 on the left hand side x by x minus zeta and y by y minus eta, you will get the expression in equation number 9. So you see that this kappa which we call is as the point spread function for the Fresnel diffraction formula. So you know that this will enable, this kappa which is given in equation number 10 will enable us to write the formula in equation number 9 in the convolution form. So the convolution form of the integral of the Fresnel diffraction formula is given in equation number 11. So u of x comma y is equal to double integral from minus infinity to plus infinity u of zeta and eta is the field at a general point x at a general point zeta and eta in the zeta eta plane, and you know that multiplied by the kappa which is x minus zeta and y minus eta, and the integral is with respect to d zeta d eta. So you see that x and y are the coordinates at the point of observation, which is p naught. So this is applicable to the linear invariant system. So you know that this is, if you recall the calculus, you will find that this integral on the right hand side is nothing but the convolution integral. So we can write it into the symbolic form for the convolution, which is given in equation number 12. So the Fresnel diffraction formula in symbolic form, that is equation number 11 written in the symbolic form, is given by equation number 12. So u naught is equal to ui convolved with kappa. Ui actually stands for the field at the input, which is u of zeta and eta, and u naught is the field at the output, which is the point p naught, that is the point of observation p naught, and you know that convolved with the kappa. So this is actually the symbolic form of the equation number 11. So when you encounter this equation in the convolution form, it means that we are talking about the true value of that symbolic representation, which is given in equation number 11. Okay, we have explained u naught, which is the u of x comma y, the field at the point xy, and ui is equal to the u of zeta eta, which is the field at the point zeta and eta. For another important form of the Fresnel diffraction formula, let's expand the argument of the exponential function as. So you see that we are going to further expand the exponential form, that is the exponential form over here in equation number 9, because this is one of the Fresnel diffraction formula. Now we want to write down another form of the diffraction formula. For that one, we are going to do an expansion of this term in bracket, in the curly bracket, that is curly, in the curly bracket we have x minus zeta whole square plus y minus eta whole square. So let's process this in order to write another form of the Fresnel diffraction formula, which is given over here. For so we have the same form over k over 2z, and within the curly bracket we have x minus zeta whole square plus y minus eta square. So you see that this is a symbolic mathematical expansion. We have expanded it, and in the last row we have equation number 13. But you know that before that we have in the third row you see that x over z we have introduced, and because we have written k is equal to 2 pi over lambda, and we have sent lambda inside the parentheses, and we have x divided by capital Z, and similarly we have divided y by capital Z, and we have replaced x over capital Z by cos of alpha, because cos of alpha is the direction cosines, and we have y over z represented by the cos of beta, another direction cosine parameter. So you see that then cos of alpha over lambda is equal to fx, that is the Fourier frequency, that is the x component of the Fourier frequency, and similarly cos beta over lambda is fy, which is the Fourier parameter in the y representation. So the diffraction formula equation number 9 with the help of equation number 13 takes the following form. So you see that this formula, which was in equation number 9, we have expanded form of the exponent e to the power iota k over 2z and multiply within the curly bracket we have done. So we have expanded that one, and using those expansions which is given in equation number 13, if we plug in this equation number 13 in the exponent form over in equation number 9, we get this formula. So you see that this is the same formula as given in equation number 9, but in another form. In the expanded form you can see. So this is another formula which is another form of the Fresnel diffraction formula. So let's read this formula. U of x comma y, that is the field at the point xy, is equal to e to the power iota kz over iota lambda z multiplied by e to the power iota k over 2z, and within the bracket we have x square plus y square. This lies outside the integral, and within the integral from minus infinity to plus infinity we have within the curly bracket u of zeta comma eta multiplied by e to the power k over 2z, and this is zeta square plus eta square multiplied by e to the power minus iota 2 pi fx into zeta plus fy into eta, and integration is with respect to d zeta d eta. So you know that here we have two quadratic phase factors. One is based on x square plus y square lying outside the integral, because it does not depend on the parameters of the integration, and there is another quadratic formula lying connected with the object plane. So this is zeta square plus eta square. This is connected with the object plane, and on the left hand side we have e to the power iota k over 2z multiplied by x square and y square. This is another quadratic term which is connected to the output plane. And you know that if you identify this integral within the curly bracket and the other terms which are outside the curly bracket, you will identify that this double integration is giving you the Fourier transform of what is contained within the curly bracket. So we can write in equation number 14 in the second step a Fourier parameter, and within the curly bracket we have the quantities which we have shown. So this is the Fourier transform of u of zeta and eta multiplied by e to the power iota k over 2z, and within the bracket we have zeta square plus of eta square. So this is actually the Fourier, this is actually the representation of the Fresnel formula in the Fourier form. So you see that we have in equation number 14 on the first row we have the expanded form of the Fresnel diffraction formula, and in the second row we have the Fourier representation of the Fresnel diffraction formula. So it means that we have discussed three formulas in principle. One is based on equation number 9, the two more formulas are based in equation number 14. One is the expanded form of the Fresnel diffraction formula, and the other is the form of the diffraction formula which is based on the Fourier of the input field multiplied by the quadratic phase factor at the input plane. So e to the power iota kz, which is outside this one, for a given z is constant and can be dropped. And you know that if this formula gives you the amplitude at the output plane, so if amplitude is not important, we can drop out the constant phase factor, which is e to the power iota kz. But we cannot drop e to the power iota k over 2z into x square plus y square, because when at the output when x and y change, then of course this factor will change. But the other factor, which is e to the power iota kz, for a given z it is constant and can be dropped. especially when we are talking about the measurement of intensity. So now we are going to explain some terms contained in equation number 14 in further detail. So e to the power iota k over 2z into zeta square plus eta square is a quadratic phase factor and is associated with the coordinates of the fictitious point sources located within the diffracting aperture. Now e to the power iota k over 2z multiplied by x square plus y square is the second quadratic phase factor and is associated with the coordinates of the output or the observation point. 1 over iota lambda z is a scaling factor which is constant for a given z. 1 over iota is equal to e to the power minus iota into pi by 2 is another constant phase term independent of capital Z. And you know that this is nothing but is the Fourier transform, that is the Fourier transform operator operating on the curly bracket containing u of zeta and eta e to the power iota k over 2z multiplied by zeta square plus eta square. This whole term is actually the Fourier transform of the amplitude of the fictitious point source located within the clear aperture multiplied by the position dependent quadratic phase factor. So equation number 9, equation number 11 and equation number 14 containing two forms of this one. So there are total of 4 forms of the Fresnel diffraction formula, are the different forms of the Fresnel diffraction integrals or the diffraction forms, and any of these can be used to compute the Fresnel diffraction. Now further detail, you see that we have expanded R01 while writing the Fresnel diffraction formula. We have used some approximation there, that is we have used in the denominator R01 was replaced by capital Z, and in the numerator where we have e to the power iota something and also R01, there we have replaced R01 by in the expansion of the binomial series by the first 2 terms, and we have rejected the third terms because we were assuming that the third term is not contributing much to the phase variation, and that there was also a limit in the third term. Third term was also limiting the value of z, so that we can remain within the Fresnel region. Otherwise, if we increase further z, we shall violate the Fresnel region, and we shall go beyond that. So you know that this is the R01 in the center, the solid curve of the R01. And you know that we have the dotted line outside of this one, which we have referring as the first 3 terms in R01. And you know that we have a solid, we have a dotted line facing towards the point P1, point of observation P1, that is going like a parabola. So this is the first 2 terms in the expansion of R01. And you know that we have also shown a planar region just against the point P0 located on the z-axis. So about the z-axis, which is passing through the center of this planar region, you can see that this small width is the width of the planar region, or we can say it a planar aperture. So let's read the statement. The first 2 terms and the first 3 terms in the expansion of R01 are plotted at the location of the diffracting aperture viewed from the axial point of the observation P0. The surface labeled R01 is a sphere, and the surface labeled first 2 terms in R01 is parabola. So R01 is actually a sphere. The first 2 terms in that figure is actually a parabola, and you know that the third term which we have ignored, but we have shown also it there in the figure. In equation number 14, we thus assume that the shape of the diffracting aperture is a part of a parabola. So you know that since we have used only the first 2 terms in the expansion, it means that when we are talking about the Fresnel diffraction formula, it means that we are talking about which region we are talking about? We are talking about the parabolic region of this curve. The size of planar region extends or shortens as the point of observation moves away or approaches the aperture. That is when R01 increases or decreases, and according to that one, the linear aperture will increase or decrease, because you know that the size of the sphere will increase, and of course the planar region will also increase if you increase the value of the radius R01. And if you make it smaller, that is if you make R01 radius smaller, P0 will come closer to the aperture, thus the sphere will be more curved and the planar region will be smaller. The size of the planar region extends or shortens as the point of observation moves away or approaches the aperture, that is when R01 increases or decreases. For a given size of the aperture, as long as the diffracting aperture appears parabolic to the point of observation P0, then P0 is said to be in the linear field, in the near field or Fresnel diffraction region. When P0 moves away from the aperture surface, the surface starts becoming planar and P0 is out of the Fresnel region. So you see that here we have very much explained, very clearly explained that for the Fresnel region we have to have this curve in the parabolic path. But if P0 moves further away, then we have a plane region in that one. That is, we are talking about the plane region. In that case, we are not in the Fresnel region. So as far as we are talking about this region, which is parabolic, it means that we are in the near field or in the Fresnel region of the diffraction. That is the formula, that is the Fresnel diffraction formula will be applicable in that case. So let's read that statements once again. For a given size of aperture, as long as the diffracting aperture appears parabolic to the point of observation P0, then the point P0 is said to be in the near field or the Fresnel diffraction region. When P0 moves away the aperture, the surface starts becoming planar and P0 is out of the Fresnel region. A larger sized aperture will produce Fresnel diffraction up to larger distances, and a smaller sized aperture will produce Fresnel diffraction up to shorter distances. So this is very important point. The size of aperture and the distance of a point of observation from the surface are two main parameters to set the region for near field or the Fresnel diffraction. Analysis of the Fresnel integral, equation number 9. So you know that we are going to further analyze the Fresnel integral given in equation number 9, but here we are going to give a one-dimensional representation of that integral. So u of x is equal to e to the power iota k z over iota lambda z, the single integral from minus infinity to plus infinity u of zeta, that is the field only at a single coordinate zeta, multiplied by e to the power iota k over 2z and multiplied by e x minus zeta whole square with respect to integration with respect to d zeta. And you know that we have represented another form, but in the variable we have written the variable in the exponent. We have changed the variable, that is we have replaced k by 2 pi over lambda, and we have changed the order zeta minus x rather than x minus zeta, because that would not make any difference because of the square we have taken. So equation number 5 is very important, because you know that we have to solve this equation. For what we are going to do or analyze this equation. In order to analyze equation number 5 or 15, we have to do some settings. That is a setting zeta minus x is equal to t, and d zeta will be equal to dt, and lambda z, the scaling factor is set. We are setting that one equal to 1, because in the physics this scaling factor would not change the physics. And we are omitting the constant phase factor at the left hand side of the integral e to the power iota kz, because this is one reason is that it is outside the integral. The second is that it is based on k and z, both quantities are constant for a given z, and so we can omit this one. So equation number 15 takes the following form given in equation number 16. So u of x is equivalent to 1 over iota single integral from minus infinity to plus infinity u of x plus t e to the power iota pi t square and dt. So you see that we have written the integral number 9 in one dimensional form and in this form, so that the analysis becomes easier and we can analyze it, because the plot of one dimensional quantities can be appreciated very well. Now you see that we assume that u of x plus zeta is a smooth function that is varies very slowly over the aperture plane. It is not a grating function which is changes abruptly, but any scene, any natural scene, for example, or any scene that looks like very natural. So u of x comma t is a smooth function that varies very slowly over the aperture plane, and the main contribution to the integral will arise from the function e to the power iota pi t square. So what we have done is that we have taken u of x plus t outside this integral, and we are taking the absolute value of that quantity, that is the absolute value of the quantity on the left hand side and absolute value of the quantity on the right hand side. So both absolutes we have taken. One is around the quantity outside the integral, and we have also taken the quantity. We have also taken the absolute value of the quantity within the integral, and the integral is not from minus infinity to plus infinity, but from minus x to capital X. Okay, so we are dropping the coefficient with the integral, and we are just writing the integral only because we are interested in to analyze the integral, especially the term which is in the exponent form, that is e to the power iota pi t square. So you know that the solution of this integral is nothing but in the form of Fresnel c and iota times Fresnel s. And you know that the solution of this integral is given in a constant form, that is square root of 2 multiplied within the parenthesis Fresnel c, and the argument of that Fresnel c is square root of 2 multiplied by capital X plus iota times of Fresnel s, and the argument of that one is 2 square root of 2 multiplied by capital S. So you see that I have introduced Fresnel c and Fresnel s integrals in one of the very earlier slides. So you see that I have represented this integral in equation number 17. Fresnel integrals appeared in equation number 17 have been defined earlier. So you see that now I am going to give you the plot of that integral. Fresnel integral appeared in equation number 17 has been defined earlier. So plot of the absolute value of u of x, because you know that u of x contains complex variables also, that's why we are taking the absolute value of the output intensity being a single parameter, because it is complex amplitude. So absolute value of u of x for positive values of x is shown, which is symmetric for the negative values also. The main values for the integral is confined in the interval from x in the region from minus 3 to minus 3 to plus 3. So you can see that in the plot that the main fluctuations of this integral rises from 0 to a value about 1.3 times, and then you know that the integral values are the amplitude is fluctuating and also reducing in amplitudes, and ultimately you see that this becomes equal to 0, and we can see that over main values of this integral the fluctuations are very noticeable when we are in the region from minus 3 to plus 3, that is a capital X in this region. The integral approaches an asymptotic value of 1 for large values of x. So you see that if you go beyond the value of x greater than 4, this integral will fluctuate, and with the diminishing value of these fluctuations, and ultimately the integral will converge to the asymptotic value equal to 1, which has been shown in dashed line in this figure. The integral has a similar behavior for negative values of x. Beyond this range, symmetric and rapid fluctuations make the integral to vanish. The output Fresnel field thus lie in a localized values of the output field. So you see that due to very small variations in the integral would vanish for large values of x. So we can say that the main values of x of the integral will exist between minus 3 to plus 3. The output Fresnel field thus lies in a localized region of values at the output plane. Second visualization of the Fresnel field distribution. How does the input field u of zeta eta contribute behind the aperture at a distance z0 from it? So we have, let's find the answer of this one. Choose any point P0 behind the aperture at a distance Z0 from the aperture. Join P0 with the corresponding point P1 on the aperture such that the line joining P0 to P1 is perpendicular to the plane. So you see that P1 lies in the clear aperture, P0 is the point of observation. So join these 2 points. The distance between P0 and P1 is Z0. So join these 2 points together, such that P1 is located in such a way that P0 and P1 are located at the same height from the z-axis, above the z-axis, so that P0 joining P0 to P1 makes a line which is perpendicular to the input plane. So P0 to P1 is perpendicular to the plane containing the diffracting aperture, that is the zeta eta plane. Now this is very important. Draw a two-dimensional square of side length. So you see that we are talking about a two-dimensional square, each side of which one has a length equal to 4 multiplied by square root of lambda z. And lambda z is the same quantity, you know that the fixed value is z naught, but you can we have kept it in the general form, so you can assign it any value of z1. And you know that when lambda is fixed, but when you change the value of z, what will happen? The dimensions of the square will increase or decrease. If z increases, then the dimensions of the square, the square that we are drawing, will increase in size. And what is the center of this square? This square is located at the point P1. So it means that we are drawing a square of dimension of length of size equal to 4 times square root of lambda z, centering at the point P1. So we have written over here centered at P1. If this square is fully contained within the open region of the diffracting aperture, the point P0 will be located in the region designated as a light region. If the square is intercepting partly the open region and partly the opaque region of the diffracting aperture, the point P0 is said to be located in the region designated as a transition region. For example, in this figure. So you see that if our square aperture is contained fully within the clear aperture, we are in the light region. But if you go further away, or if you go away from the z-axis, you know that the z-axis is passing through the center of this figure. If you go away from the z-axis, then you know that what will happen? You may be falling in the transition region. So in the transition, what will happen? That is, the square that you will draw is intersected by two regions. One is the clear region, the other is the opaque region. So part of the square aperture is lying in the clear region, and a part of that one is lying in the opaque region, which is shown by the dark lines over there. So due to that one, we will say that our point of observation is in the transition region. And if you go further beyond, away from the z-axis, you might be falling in the dark region, where your aperture, that is your square aperture, will fully contained in the opaque region of the diffracting aperture. So if the square is fully contained within the opaque region of the diffracting aperture, the point P0 will be located in the region designated as a dark region. Transition regions are the parabolic regions, with the light and dark regions located outside these parabolas. So you see that, look at the shape of the transition region following a parabolic shape. The dark region is outside on both sides, and you know that these transition regions are containing light regions which are contained within them. For the above analysis to hold, the following conditions should be met. Number 1, diffracting aperture has a transmission that is slowly varying both in amplitude and phase, or equivalently, there are no fine structures within the diffracting aperture. So in order to hold for this figure 1, for the figure that we have shown, the condition 1 must be satisfied. The condition 2 is that illumination should not contain abrupt variations in amplitude and phase, or equivalently, the illumination should preferably be smooth plane waves. The third condition is that the point of observation, the point P0, is located in the Fresnel region. Finally obtained. So we have equation number 20. Let's see, we have equation number 17, and now you know that we have equation number, we have to find equation number 19.